afternoon.
Hello.
Okay, good evening. Right, so welcome to this special lecture by the ADY Professor at Large, Shri Kulkarni from Caltech. My name is Dong Lai from the Astronomy Department. So let me first say a few words about the ADY program. And Penny is here. Want to say something about this? This program was established in 1965 in celebration of Cornell's first centenary. It was named in honor, of course, of the first president of Cornell, Andrew Dixon White. There is actually a program website on the internet you can look up for the details. But let me just quote from the website. At any one time, 20 outstanding intellectuals from across the globe hold the title of ADY Professors at Large and are considered the full member of the Cornell faculty. During the 6-year term appointment, each of the professor at large visit campus for about 1 week in each 3-year period during the academic year with a single mandate, one job to do, namely to enliven the intellectual and cultural life of the university. So that's the goal of the program. So again, you can look up this website where you can find a list of all the distinguished visitors or professors that have come through this program over the years. So the names are very impressive. Today's speaker, Shri Kulkarni, or Shri, as he's widely known to the community. It's one of the most eminent astronomers in the world today. And I would say he has been pretty famous for the last 30 years since he received his PhD with the discovery of Micheslon pulsars. These Micheslon pulsars are the neutron star with solar mass, but sort of spinning once every millisecond, so pretty fast exotic object. He discovered that when he was a student, so immediately became a star, basically. So over 30 years, he has continued to make all kinds of discoveries. So Shri got his undergraduate degree in India and PhD from UC Berkeley. He is currently the McArthur Professor of Astronomy and the Professor of Planetary Sciences at Caltech. He's the director of the Caltech Optical Observatories and also the director of NASA Exoplanet Science Institute. His research accomplishment is well known, covering some of the most dynamic, interesting areas of modern astrophysics, including neutron stars, pulsars, gamma ray bursts, all kinds of explosions, exotic explosions, brown dwarfs, these are stars that failed to make it into a star. The star tried to become a star but failed to make a star. And also technical problem of trying to use interferometer adaptive optics to detect exoplanets and many other things. He has more than, he just told me, he has 59 papers published in the journal Nature. And so for those of you who don't know, Nature is a very top international journal that publishes only new discoveries. So new flashy discoveries. So not necessarily all discoveries are but all important, all discoveries. So 59 discoveries. That's a lot of discoveries over 30 years. That's quite impressive. Shri is a member of National Academy of Science and Fellow Royal Society. He has received many awards and honors, which I have to skip today. Shri has actually visited Cornell many times in the past. He did his PhD thesis here that was partly done at Arecibo, where Arecibo is a radio telescope operated by Cornell at that time. And that's Arecibo, Shri made the discovery of, co-discovered the Micheslon pulsar that I mentioned earlier. Okay? And he was a saltpeter lecturer in our department some years ago. This is a lectureship in honor of one of our distinguished former colleagues. So Shri has many friends and close colleagues here. So we're always very happy that he can visit. Shri was elected to the ADY Professor at Large 6 years ago. So this is his second visit under this program. During this week, he will participate in various activities, including guest lectures, meeting with graduate students, meeting with undergraduate students, and so on. He just attended our informal faculty lunch meeting, where he made some interesting remarks. It's very stimulating. So he's fully engaged as the program envisioned. Okay? So, needless to say, we hope that he will continue to visit us in the future and bring the excitement to us, to Cornell. Okay. So I think I've said enough. So let's welcome Shri, and he will talk about dynamical side. Oh no, bump and boom burps. Shri. Yeah.
So my wife unkindly remarked to me when I said, Cornell has given me this great honor of being an AD-wide professor at large. She said, you mean you're a large professor at Cornell? And I told her I can't help it. As you get, don't you know, and I'm sorry, this is an astronomical joke, that dark matter goes to the bulge. But anyway, sorry. Okay, so I'd like to, the nominal title is the dynamical optical sky, and the more figurative way of saying that there are bumps, booms, and burps in the optical sky. And today we'll mainly talk of booms. We'll skip the bumps and burps for future. The talk has actually two strands. One is the obvious astronomy part, which is about how the night sky keeps changing and what we are learning from that and why is that an exciting field. And the other part is something I think a lot. I have a strong belief that if you want to be a good researcher, then it's very important to identify interesting problems. The solutions are much easier always, but identifying interesting problems, by which I mean which can be solved in a few years, preferably 2, 3, and which others care about, not because you happen to be particularly interested in that object or that particular subject, and it should be genuinely adding value. So I spend a lot of my time thinking about it. So there's a little bit of that underneath, and I hope you'll get a sense of that. And also I'd like to thank some young people who were bused to this meeting, to this talk, because they'll get some credits. And I can assure you, you may not fully understand some of these things, but at the very least, the entertainment will be at least better than the education. Okay, so let me start off with the first thread. So this is the first part. It has nothing specific about astronomy. So my thesis is, and this may surprise many scientists, and I would say mainly research of the sort I do. I don't do what I'd call as contemplative research. I don't go into a room and sit down and think, let's now come up and quantize gravity by pure thought. That's not, but I'm talking mostly research done by most people, It requires devices to be built, measurements to be made, hypotheses, that sort of routine things. The sort of stuff most Nobel laureates end up doing anyway. So I would claim this sort of research, which is 99% of the research done at places like Cornell or Caltech, I would claim it is, the progress in that is entirely driven by technology. That is, you could knock off any astronomer. You could knock me off, and the course of astronomy will not change. But what will change is if there are technological revolutions. Okay. Now, of course, this demeans the particular researcher or researchers as people. It's okay. That's how large these changes are. Okay. So I hope at the end of this thing, some of you will stand up and say this is absolutely false, and really people make changes. But I'd love to argue, as you might have gathered from Dong's introduction. Nothing delights me more than arguing, and in fact, arguing against myself is even more sometimes pleasurable. Okay. Okay, so if you accept my hypothesis, which let's do for the next 20 minutes, then I would say that let's look at when can you have huge technological changes. I would say there are actually two important changes that have happened in our lifetime. The first one is exponential growth. We all agree if you have an exponential change of anything, that's like pretty important. It can be disastrous, it can also be very important. And the most famous exponential growth that we are enjoyed in our lifetime is, of course, given by the called as the Moore's law. And this is real data. I know there will be very few social scientists here, so I could actually go ahead and start doing my thing that everyone expects me, which is to more or less make some snide remarks about other fields. Since this is, you should always talk, hypothesis should be based on data, not on ideology. So Moore's law is a real observation. It's not some simple idea that something has to be right. So what Dr. Gordon Moore, who co-founded Intel, noticed in the mid-60s was if you plot as a function of time the transistor density on integrated chips, they follow a line. This is a log plot on the y-axis and linear on the x-axis. It follows a straight line, which means it's doubling at a certain constant rate. And the doubling time here is 24 months. And for some of you who are old enough, these are very memorable chips, 8080, 8086. In fact, I'm still excellent. If you need an assembly language program in 8086, I can do it really, really well. Okay, then the 386, and then you get on to the more modern chips. Okay, well, so Moore's law is, we all take it for granted, but, and I won't touch upon the larger issues of what this means for our ordinary life, other than it really has affected your life and my life. So let me now just focus and justify my hypothesis by saying, okay, how has the exponential growth affected astronomical research? Okay, here's an aerial view of the Palomar Observatory, of which I'm the director, and it's about 125 miles southeast of Caltech, up in the mountains east of San Diego. And we have a bunch of telescopes, and this is the iconic 200-inch telescope. And this is the 48-inch Schmidt telescope, which I'll refer to. And 18-inch Schmidt, which was the first telescope, came about, and 16-inch student telescope. Okay, so it's been around for about 63 years at this point. And this telescope, which saw first light about 1950 or so, can take images of large pieces of sky. That's its specialty. So the astronomers immediately started cataloging the sky. That is, they took systematic pictures of the sky starting in the mid-50s and stretched for about 20 years to complete two-color image of the sky. That means you obtain the picture of the sky in, let's say, red color and in blue color, because some stars are red, some are blue, and you learn something from the colors alone. It took a long time because, and some of the young people, I do see a few young people, you use something called a photographic plate. It's a thing you hold in your hands. It's got a silver halide on a glass piece, and then you expose for an hour because it's not very sensitive. Then you take it down to a dark room, you put some chemicals, and after a while it's very noxious, foul-smelling chemicals. You hang it to dry, and you see the stars as appearing inverted. So the bright stars appear as black spots, and so on. Okay, and then the astronomers took rest for a while, and then they did another sky survey, called Palomar Observatory Sky Survey number 2, and that took another 20 years, this time in 3 colors, because meanwhile, the film technology had actually improved, so you could, in the same time, do 3 colors. Okay, well, that's an heroic undertaking to catalog the northern sky as it was in, let's say, circa 60s and 80s. Okay, so if you now go into the 90s, this is the 2-micron all-sky survey, a rather clever acronym here, because it was promoted by the University of Massachusetts. This is shown in the usual coordinate system, where this is the equatorial plane, and this is the North Pole and the South Pole. And what you see here is a picture of the sky, and not in optical, but in near-infrared wavelengths. Let's not worry about that distinction. But this took only 5 years. It used electronic detectors. There are no photographic plates, they're far more sensitive. The data was already digital, so you didn't have to scan the photographic plates and so on. Well, this couldn't have been done, this survey couldn't have been done without Moore's law operating for astronomers. It required advances in, it required the fact that these detectors could be made cheaply so astronomers can buy them. It required inexpensive computers so you can reduce the data, store the data, and so on. So right away I've shown you that technological growth made a huge change to astronomy. Okay, now less spoken about than Moore's law is a bunch of things that unfortunately can't be just called as one thing, but which I think is actually very important. And I'll just simply call it as automation. Under automation, I list robotics, multiplexing, which is instead of getting one channel of data, you get many channels at the same time, and then machines talking to machines, okay, which is sort of robots talking to robots. This is not as well known or well taught, but it actually has, in my opinion, a far bigger effect, not just unfortunately in astronomy, but or fortunately for astronomy, but unfortunately I think it has a big effect on with implications for actually the rich countries, but that's not the talk here. So let me show you some examples of what this is. So Caltech also cooperates the Keck telescope located in Mauna Kea in Hawaii. So I go to Hawaii quite often. And there are some of these old buildings. You know, here's an old old grocery store which is now being made into an art gallery / cafe. And you may not be able to see because I think if we could dim these lights a bit, that would be, in fact, thank you. So you may not be able to see, but that's a fan. It's whirling around. That's why it's a bit. So there's a fan here. There's a fan here. There's another fan here. And these fans are they're driven by there's a motor here, and this motor supplies the motive force with these ropes that they supply power to this, you're carrying the mechanical energy, really, literally. Could someone venture, I'll wait for 30 seconds, could someone tell me why this building has this arrangement by which you have these fans fed by this motor? Okay, I know that many of you know the answer, but probably very shy about it. The reason is, 100 years ago, making motors was very expensive. They're all handmade. You'd need really fine wire to wind up. The materials so expensive. And therefore, you bought a single motor, and then if you wanted fan in the entire big hall, you distribute it by ways of rope and pulley. Okay, you buy a simple camera, practically a throwaway camera. It has many, many motors in it. The number of motors has actually exponentially increased in 100 years. It's not been so noticeable. Well, you can even buy a $2 hair trimmer, which sometimes I use for my ears. It's got a motor. So motors are like really, really cheap. And this has had huge effect. So I like visiting, when I go to places which I do travel, being the absolute Philistine I have no interest in art galleries and other such things. But I do like to visit museums for manufacturing and other such things. So when I was in Japan last year, I made a point of going to Nagoya to see the Toyota factory. And that's amazing. The most amazing thing I felt was you see this assembly line, and there's no one there. There's no one there. So this is machine-making machines, and these are immense robots which can actually make, which really are very complicated. It's really almost mesmerizing to see this arm whipping around at very high speed with precision. Okay, so I think this is a real effect. Okay, there are some obvious implications about who will be having the money to buy these cars if you displace the workers. But anyway, that's, again, as I said, not a talk for here. But this effect has had, in astronomy, a huge effect. That astronomers would, for example, get a spectrum of a star one at a time. But now, we actually incorporate a lot of these effects. So a telescope has a focal plane, let's say, of this size, physically. Then there are lots of stars in that field of view. Then you can have a little robot that actually positions, or a positioner that can take a fiber and put it at this star and that star and that star. So all of a sudden, instead of getting a spectrum of one star, you can get 400, maybe 4,000. Okay, That's high multiplexing. And you couldn't do that if you just humans were there plucking away one at a time. These things are really done like this Nagoya robot. They actually precisely aim, align themselves. As a result, the amount of data that astronomers are getting from this sort of part, other than Moore's law, is really changing, and it's exponentially growing. Okay, so I hope I've convinced you that research is by and large driven by technology, and technology seems to be accelerating, and there's this other part that normally is not appreciated. Now let me get to more of the present talk, which is, first of all, let me start by saying astronomy is in a fantastic growth phase. I think if you ask me what are the fields that really are exploding literally, astronomy has been amazingly productive. Another field that's really, really productive is biology. Now, I do hope there are a few physicists in the audience because I'm sure they'll appreciate this. I won't tell you the sign of their appreciation, but let's say in the 60s, if you said, well, what is interesting? The 60s was the era of high energy physics. People are discovering new particles. It looked very exciting. There's some theories, there should be a particle here if the symmetry held, and lo and behold, 2 months later, a particle was found. I wouldn't say that's the same thing today. I mean, the last press release from the LHC was LHC will be shut down for 2 more years while we refurbish something. Well, I was thinking, that's an amazing press release. It's like me putting a press release saying, we are shutting down Palomar for 1 month while we are recoding the surface of the mirror or something. Anyway, so the idea that exponential growth always happens is not true. Okay, and there's a reason why biology and astronomy, and they share something in common. Both are highly phenomenological subjects that they're in an explosive growth. And that growth is being driven by technology for the 2 reasons I went into. Well, my view is that astronomy will probably enjoy a golden period, for this decade and perhaps beyond. It's very hard to predict, as you know, the future. Within astronomy, as I said, I do always want to think of what's the next easy project to do. When I say easy, I mean something where you can achieve something in a short order, okay? There are several areas, of which one, in my opinion, is time domain astronomy. That is, to go back and visit the same piece of sky, and what do you expect to find? Either you expect to find a new source, namely an explosion, a supernova, or a source that moved, which means objects in the solar system. Okay, and the reason this is interesting is astronomers practically across the electromagnetic band spectrum have imaged the sky to some very interesting levels now. So it's hard to just go and make yet another image of the sky. So most of the studies of that sort are to find interesting objects or patterns or structures. Whereas this time domain astronomy is, therefore, so most of that sort of science has become archival, where astronomers, in fact, don't need to go to a telescope. They can download a whole picture of the sky, for example, done with the Sloan Digital Sky Survey, and then look for whatever sorts of measurements they do. But if you want to build new gizmos and do new things, time domain astronomy is the way to go. Okay. So in time domain astronomy, there are 2 areas. One is, when I say synoptic, it means the ability to image a piece of sky, large piece of sky again and again in a manner that determined by the astronomers at optical wavelengths. And I'll use an example. The exemplar is the Palomar Transient Factory, which is something I've been involved in for about the last 5 years. And you could also have something in radio wavelengths, in particular the meter wave band, and this is it's undergoing a renaissance mainly because it's entirely driven by cell phone industry. Every cell phone you buy makes radio astronomy in this band easier. Filters which used to cost a few dollars now only cost a few cents. You can integrate actually both RF, IF, and digital on the same chip, and that's what allows you to make arrays, huge number of arrays of thousands and thousands of dipole arrays. And another one that's interesting is submillimeter astronomy, and this is less to do with any technology, simply to do with actual better understanding of how to make these devices. But anyway, I don't have 2 hours to go through these 2, so you'll hear only on the first part. Okay, so let's focus on the optical sky, and we'll ask the question, what sort of explosive events do we see in the optical sky with these machines? So let me take you back to the origin of the subject, and that is, I would entirely credit to this person called Fritz Zwicky. when the Rockefeller Foundation gave Caltech $6 million in September of 1929 to build the 200-inch telescope. And Caltech then had a wise policy that as soon as they gave any instrument of finance, they immediately convert to cash, which is just as well because a few weeks later, to those who are readers of history, you should know what happened in late October of 1929. So Caltech was sitting on $6 million of real cash, and so they started the 200-inch project, working with Carnegie Institution, and then they decided they really should have an astronomer, because this is an astronomical project. And he was the first astronomer to be hired. He was an amazing person. He is well known for his contributions to philosophy. He holds fundamental patents. He held fundamental patents on jet engine, contributed greatly to the World War II effort, and he was a theorist of the finest kind, sort of person that I'm sure that both Tommy Gold and Ed Salpeter would have really loved chatting with him. And in addition, he did his own observations. I must say that someone like me actually, could barely do one of those things I just mentioned. He was also, unfortunately, not a particularly, apparently, a delightful person to talk to, and that may explain why he's not as well known as some other people. In any case, when a German optician called Bernhard Schmidt had figured out a new way of making images with a telescope of large pieces of sky, Zwicky understood its value. So working with Walter Bade, they decided to basically do the first Schmidt camera in the world, and that is the 18-inch Schmidt telescope at Palomar, the little observatory I showed. And so Bade and Zwicky began a systematic survey of the sky, is to image the same piece of sky, go back the next day, next week, or whatever it is, and then actually make a controlled experiment. And they very quickly discovered that until then astronomers used to use the word nova stellar, new star, for anything that came up new. And I started off with a slide which showed obviously the appearance of a new star. And then they showed that the so-called nova, in fact, there are two kinds, nova and supernova, meaning the supernovae are much, much brighter than novae. And that began the field of supernovae, which is an important area. Okay. So this is the 18-inch where all this work began. It's finally been decommissioned, by the way. This has had many interesting findings, the last one being Comet Shoemaker-Levy, which I'm sure all of you know about. So let's see, what is a supernova? There are somewhat different families, but the most dominant family of supernova comes from young stars. So here's a picture of a Messier 51, also known as the Whirlpool Galaxy, and here's a new star that has appeared, this time July 7, 2005, and that is if you took a picture a few days before that, you would have not seen this bright star, then you see a new one. And this galaxy is rather fertile in making supernovae, because here's one in 2011, another new star. And these sort of, which we call as core collapse or supernovae from young stars, they really result from the deaths of stars, let's say 10 times or more than the mass of sun. Okay, so massive star dies. Why is that so important? Well, as Carl Sagan would have said, we're all children of stellar dust, but we're all children of stellar ashes. And I have to say, for the lone chemist who may be in this audience, astronomers have a rather loose view of chemistry. We believe the universe, we in fact can prove to you that the universe began with hydrogen and helium. Here's a periodic table, hydrogen, helium, and a bit of lithium, which is just a little bit. But that was important because lithium is very fragile, so you tend to destroy it. You can't make more of it. And I don't know about Cornell, but at Caltech, the lithium is an important thing, especially given some of my colleagues. Okay, well. Okay, anyway, apart from that, hydrogen, helium, lithium is minor. The rest of the periodic table, the rest of the elements, we simply call them as metals. I know these are not metals the way you define, but it's the stuff that happened after the universe began. And all this periodic table gets populated thanks to stars dying. So all of you should be very thankful that stars died, because otherwise you won't be here. A universe full of just helium gas bags or hydrogen gas bag, I don't think would be very interesting. The deaths of stars is what creates the rest of the periodic table. Okay. So anyway, the few the high school students who are, I know, attending this for getting an extra grade, you put this down, your teacher will be very happy. They'll know you learned something. Don't tell the teacher about the lithium joke, because the teacher may not share the sense of humor I have. Okay, so why should one search for cosmic explosions? I would say the simplest idea is it's a curiosity. You know, as I said, the job of astronomers is like a biologist, is to go and explore the universe as we know. So we go and look at weird and new stuff. That's what we should be doing. This idea of phase space, of the way of looking at discoveries, actually, this concept was introduced by Zwicky himself. Until then, the term phase space in the way it's now used is thanks again to Zwicky. So let me explain what I mean by that. So phase space is simply a graphical way of, when you find something new and you're simply trying to form an idea what it is, then you take some parameters. So for example, let's say you discover, you want to go and, the simplest phase space I can think for human beings is, mass and height. Okay, they're obvious big physical attributes. Then you can plot, for each person, you put a dot where their mass and their height, and then you'll actually start discovering some regularity, okay? And you'll learn something. This is the first part of cataloging things. So the phase space here is, and in honor of Zwicky, I'll simply call it the Zwicky diagram, is to plot the duration of transients on one axis, okay? So if you see an explosive event, how long does it live? Does it live for a day, 10 days, 100 days? That's what this is. And these are log units, okay? And then how bright it is on the y-axis, okay? And it's sort of negative units as magnitude. And the idea is actually, some of you might say, that's sort of a bit strange. And the answer is very simple. Now, some of our physics friends, I must say they're pretty bright people, okay? And the problem is, as I mentioned to you, physics is right now in a bit of a lull phase. And our worry is that our subject, on the other hand, it's buzzing with excitement. We can just go and make discoveries every night if you want to. So how do you keep these very bright people who don't have much to do from entering a field? Well, what we do is we convert this brightness into log units and put a minus sign. It seems to be amazingly good. Most physicists are like so stumped, they never get beyond that, which is just as well. Okay, so the more negative the number, the brighter it is, and it's not linear. Every factor of 2.5 is like 10, and so on. And here's novae. They follow a certain pattern. And here's supernovae, the so-called type 1a, which is a peculiar kind of supernovae, not the core collapse. And this is the big distinction that Zwicky noticed with Barde, is that there's a 10 to the 4 difference between the luminosity. That's why it is a supernova. Okay, so we can do a test, and I'm not going to pick on physicists alone. We'll soon get to historians, all sorts of other faculty, and not to worry. But let's finish off the last physicist's joke. So we'll keep one for string theories later, but we'll do a simple psychological test, okay? When you look at a figure like this, a phase space, and I will, again, pause for about 15 seconds so you can form your own opinion. I can, in fact, immediately characterize, or you can characterize yourself. Are you an astronomer or a physicist? And here's how it works. So look at this diagram. Let me give you 5 seconds. Absorb it fully. Formulate whatever thoughts you have in mind. Okay, now, if you are a physicist, you will say, you know what, there are 2 families here. There's a parameter, and of course, there's some variation which gives rise to this. And this parameter is conserved, which is why it restricts you to that part of the phase space. And there's another family which has a different parameter. Okay, so physics is all about reducing complexity into really strong laws. If you're an astronomer, you'll say, you know what, there's so much white space here. What do I do to go and discover new things? So right away, I've now told you who you are at this point. If you should revisit your assessment, and right away you know whether you're an explorer or a deep person who studies things deeply. And you can't be both, actually. So that's one reason. That is just, yeah, let's go find what the universe is made of. And if you write such a proposal to NSF and say, look at this diagram, I've done some interesting work in the past, and I like doing this, likely, I would say with very high degree of confidence, your proposal will be rejected, because NSF, as it turns out, does not fund curiosity-driven science, which is a bit of a strange thing, but that's how it is. There are too many people wanting to do similar things. So instead, you have to write a proposal, which the best way to win a proposal like this is to find something. You say, NSF, you spent so much money in this whatever project. It doesn't have to be useful, not useful. It has to be a lot of money they spent. If you fund me, I'll make this project even more successful. So that's the one, that's a winning approach. And that's what, of course, I did to get some money from NSF. So what are these? There are some frontiers areas in physics, which are interesting in their own right, but there's a lot of money spent in them. One is ultra-high-energy cosmic rays. So I think one of my colleagues is teaching a course on special relativity. So the few students are here, I'll make you do some special relativity at this point. So let's say I'm an ultra-high-energy cosmic ray. So I have a proton. Let's just not argue whether I'm a proton or an ion nuclei. It's not important for this problem. Let's say I'm a proton and have 10 to the 21 electron volt energy. Now, you may not understand what that really means. It is the amount of energy carried by the fastest thrown cricket ball. It turns out cricket balls can be thrown faster than baseball, just the way you throw them. That's the fastest ball thrown by a human being has 10 to the 21 EV, okay? But this is in one proton alone. Okay, so the first thing some of the students here should be worried, what happens if an ultra-energy cosmic ray comes and hits me? You won't get knocked down because it doesn't have momentum, it has the energy. So hopefully the first part of special relativity, you understood why that's the case. The second one is, as me, the UHECR, comes towards you with 10 to the 21 electron volts, what is the Lorentz factor I will have? Okay, anyone who signed up for Chernov's course here? Dave, your students missed out. Oh, okay. Okay, so the rest mass of a proton is 10 to the 9, 1 GeV. Okay, if I tell you that you have 10 to the 21 EV, what is my Lorentz factor? It's 10 to the 21 divided by 10 to the 9, which is therefore 10 to the 12. So my Lorentz factor is 10 to the 12. And what do I see? I'm coming towards you, and I see the cosmic background radiation, which is 400 photons per cubic centimeter, and each photon, again, we can go back to the black body formula. I'll tell you, we'll skip all the sigma and the KT and all this stuff. I'll tell you the answer is a few milli-electron volt photons. So there are 400 of these few milli-electron volt photons, and they get boosted now by 10 to the 12. That's a big number. 10 to the 12 times, let's say 10 to the minus 3. That's 10 to the 9 EV. Well, that's a GeV. At this point, you won't get scattering. You'll actually start producing pions because that channel opens up. So this proton will get slowed down by photon pion production, and this is sometimes called the GZK effect. And so these high-energy protons, therefore, cannot, even if something originated in the distant universe, it'll never reach you. It has a horizon limited by its losses towards you, and only the events which appear, relatively speaking, within 100 megaparsecs or 300 million light years will appear. Okay. And here's another really exotic such project, which is the IceCube project, and this is amazing. It's really exotic. This is the Eiffel's Tower, and look at this. This is like 2-3 kilometers of wire suspended below the ice cap in the South Pole, so that you can get Cherenkov radiation of very high energy particles. Another major area where NSF is invented, almost by the time it's done, $1 billion is experimental gravity. And this is a big area both at Caltech and Cornell. And so imagine you have a black hole and a neutron star, and we'll start this. This is a simulation, it's not a cartoon. We start them very close enough, then the force of the black hole, the tidal forces are high enough that you can actually stretch the star, tidally distort it, and it'll start raining down on the black hole. Okay, as you rain down on the black hole, you'll produce jets, you'll convert matter into energy, and we believe this is the origin of so-called short gamma ray bursts. But while it's spiraling away, it'll produce gravitational waves, which one hopes with the LIGO, advanced LIGO system, here's one of the interferometers, you actually would see these ripples of space-time. So the proposal I wrote was, look, and for sensitivity reasons, you'd only see them nearby. Okay, you can't find them across the universe. So for sensitivity reasons, as I said, you'll see them nearby. So I wrote a proposal. If you want to understand these things for which you already invested so much money, you should fund me. And this sort of extortion actually works better than I'm interested in curiosity. Okay, so now let me get on to this project. So every 5 years, I switch topics. Nothing particular other than I sort of like doing new things, that's all. And then once a project works really well, then like a child, I want to go and get the next toy. I mean, I think research is all about toys, but I know one shouldn't say that. Okay, so the Palomar Transient Factory is something I started about after gamma ray bursts. It became mainstream. I didn't want to work in the field, partly because I hate working in popular fields, because if you work in a popular field, then you have to be actually smart than the other people, and that's hard. So on the other hand, if you can anticipate something interesting, be a little bit of a sharpshooter, then you can be reasonably, you don't have to be smart, you just have to be lucky, and that's much easier actually. Okay, so I started this program of doing a systematic investigation of night sky. And the slight novelty I had with this project was these sorts of telescopes. This is a 48-inch, 1 meter. That's a 1.5 meter. This is a 5 meter. People are building big telescopes now. So the kind of state of art these days is 10 meters. So when you have a 10-meter telescope, you'd say, oh, what's a 1 meter good for? Well, so the slight novelty that idea I had was, in fact, to go from the idea of using a telescope into a factory. So like that Nagoya example I gave you. You know, you have a line, some station does only one thing, and it does it really well. And the next one does something really well. So the idea was to use this 48-inch telescope, which can take images of the sky, you know, and that's what it does really well. And if you take an image of the sky, about 8 square degrees, I'll show a picture, then there are very few pieces, there are only a few transients, new things, and the rest I don't care. So you analyze that data in real time, send it to the 60-inch telescope for confirmation, and then if it looks really interesting, you send it to the 200-inch for spectroscopy. So this idea of multiplying telescopes, it's not particularly original, but most astronomers were not thinking that way. And fortunately, you know, being at Caltech, there are a lot of resources. If it really then looks very interesting, then we can go to the Keck telescope in Hawaii and then do the final study. So in contrast, many of these other projects of a similar sort, they're trying to image the sky in several bands, laborious, you know, either one after another, or using the same focal plane for different colors. So the throughput of this, target throughput, is very high. We can, if we are on a fine night when the machine is tuned up, we can discover a supernova every hour, okay, which is very large. So anyway, this is the idea I had, and I was discussing this idea with a friend of mine, Lars Bilston, who's a director of KITP in Santa Barbara. And so he said, oh, I want to introduce you to someone. So this few years ago, here at Santa Barbara, in one of these cafes somewhere here, I think I met this older gentleman, and I told him this is exciting. So next day, he called me up and said, what would it take to do this project? I said, well, maybe $1 million, $1.5 million plus running costs. So he said, okay, I'll give you $1 million. I said, yeah, don't give me $1 million. Give me $1 million with a time bound of 6 months. If you don't do this, if I can't raise by 6 months, forget it. Because I really do dislike projects which take forever. To me, it's surprising that some of my colleagues can work on paper projects for 10 years and have nothing to show. Anyway, and so that's a great way to, you know, so I then went around the world and said, guys, put the money down right now, we're going to do it, or that's it. And it works. If you have time limit, things actually work. So anyway, I'd like to thank Wayne Rosing, who made his fortune in a lot of high-tech things, and whose generosity started this project. So here's the data we get. Here's a picture from the 48-inch. It's a mosaic of CCDs. It's the old CFH 12K camera. One of the CCDs gone dead. We didn't bother replacing it. Aesthetically, it's not nice. Who cares? Because we're just interested in not taking pictures of the sky, but finding new things. Here's the moon that's been photoshopped in. We don't actually observe the moon. It's too bright for us. So hardware is very important, but even more important in projects, especially in astronomy, has undergone a change. We tend to think in terms of hardware, telescope, detectors and so on. But really, these sorts of projects have, the whole business has changed. In most of these sorts of projects that astronomers now do, the most important part is actually people, okay? The hardware costs are very small. So I call that as Gray-ware. And I went around and convinced all these bright young people, because the part that actually costs the most in projects of this sort is software. And the problem with software is once you start paying money for software, there's no end to it, okay? So the deal here was simple. Come and work with me. You write pipelines. You do what you're good at. And in return, you get to participate. So all of these guys have done well. Josh Bloom, he led the machine learning algorithms, and he's a professor at Berkeley. Jason Suarez did the photometric pipeline. Then Peter Nugent is a senior scientist at LBL now. He led the imaging pipeline. Eran Ofek is a professor now at Weizmann and in Israel. And he read the automatic sequencing. So when you do, you may be surprised that when I show you this, sorry, on a typical night, there's no one running these telescopes. There's not just robotic, which is not, pretty straightforward these days. The telescopes are completely sequenced. So even if it rains out or weather is bad, the telescope, Iran's program actually reprograms itself so it gets back on when the weather clears up. So it's not like there's a grad student at 4 o'clock every afternoon saying, oh, what should this telescope be doing tonight? That can work very well for a month. Grad student will be excited, oh, I can really run this telescope. But I suspect after 2 months, they'll come and shoot me, because that's what I would do if I was in her or his position. Okay, so that's what Iran did, was to replace this automatic sequencing. Rich Dekaney, who's chief engineer in my observatory, he led this. Robert Quimby, who's now at IPMU in Japan, he was the software integrator for this project. And a young man called Nick Law was the project scientist. So all these guys had just finished PhDs, most of them. And I said, this is what you can have. And it kicked off. So the project is almost about 80% money, effort is all in software. There's a huge amount of pipelines that run at the night. So for example, the data gets taken on the 48-inch. It's the 8 microwave towers. It goes down to San Diego supercomputer, then gets onto the internet. Then streams out to Caltech and to LBL and to a DOE computer in Oakland. Various pipelines kick in. This is in Caltech. This is in Oakland. This is at UC Berkeley. They send you back information, what they have found, and then the 60 inch is automatically triggered. So this is machines talking to machines. There's no human in the loop. Because if you want to do really great astronomy, you've got to get the astronomers out of the telescopes. It's an important thing. That is a joke for my astronomy friends. Okay, I'm one of these guys. I really don't enjoy staying up and observing. I never found that interesting ever at all. I started as a radio astronomer, and my view is you program these things so that you actually don't have to go and be awake in the middle of the night. So the basic plan is simple. Of course, they're all details. You get new data tonight. You compare that data to taken previous night or the previous month or previous year. Subtract the two. It's not A minus B. There's a bit more art to this called image differencing. Well, that's a supernova. Well, here's an example where you do the same thing and you find, oh, that looks like a supernova. But if that's a supernova, well, that's a supernova too. And you know right away this is bad subtraction. So that's where the machine learning algorithms come in. And in the beginning, we had citizen scientists who would classify it for us. But now the machines do it themselves. It's a very large amount of data that comes through. We have now acquired about 4 years of data on the sky, and they're fun projects we have now begun. So I won't go into all when you have this sort of data, you really can do astronomy all the way from the solar system to the distant universe. I'll just focus on supernovae. Oh, I'm sorry, this is an old slide. We have now reached, I think, about 1,990 spectrals, that is supernovae, which we have discovered, classified, and done detailed studies. That's a large number of supernovae. When we started the project, the entire global output starting S Andromeda to when we started was about 4,000 supernovae. So for us in a couple of years to add another 2,000 is just a single project is a lot. So what have we learned from this? One of the main projects, as I said, was to explore the Zwicky phase space. So here's classical novae. Here's the so-called 1A supernovae, sometimes called thermonuclear supernovae. Here's a supernovae from those young stars I started off. And this project of finding the new supernovae was, in fact, the PhD project of a Cornell undergraduate, Mansi Kasliwal. And her job was to go and discover new things here. Of course, we are not the only people doing this sort of work. There have been other efforts, including amateurs, other groups. So you can see this is what it really now looks like. There are all sorts of new beasts in the skies. Astronomers' view of going and exploring new things is true. Some of those were anticipated, like this. Lars Biltisten had an idea that such things could exist. Some are completely new. We had no idea there would be things like luminous red novae. There are two types. I won't go into details. Just wanted to flash through. Here's some supernovae we found which are calcium rich. For some reason, they produce a large amount of calcium. Okay, in more technical terms, the nuclear burning is incomplete. And here this luminous red novae, of which there are two kinds. There are more theories of what these objects are than the number of objects. And that's exactly what an observer loves to be in that situation, where every new discovery adds something interesting. Here's something that had been theoretically considered, looks true. And here's sort of something which there are some ideas, but the richness I think had been completely unanticipated. So let me show you, just go briefly through the super-luminous supernovae. Here's a supernova light curve, which is time on this axis in days. It's traditional to call 0 days when the object is the brightest, and before that it's negative, and after that it's positive. And here's how bright they are. And this time it's in solar units. Physics friends would understand that this object, for example, is 10 to the 11 times brighter at peak compared to the sun. And here's what a type 1A, one of the brightest supernovae of the routine kind. And this supernova, in fact, is brighter at peak and lasts a lot longer. So in fact, is 10 times brighter and 10 times more energy output. These sort of supernovae with hydrogen is well known, and I can't go in details, but in some ways it's easy to understand. But the major part that PTF contributed is finding equally bright supernovae without hydrogen, and there's a lot of challenge with that. And I have to show you at this point some spectra, which one is not supposed to show spectra at popular talks or colloquia, because that would be showing like your dirty underwear, but that's sort of where the really business gets done. And that's where the telescope was essential. So what Robert Quimby, who led this study, was able to show is years ago, some astronomers had found this weird little object which looked like it was from another galaxy, but they didn't know what it looked like, and he had found something nearby. And he was able to get through PTF all these various things, and he was able to show that this super-luminous supernovae, in fact, forms a redshift sequence, and these are the brightest supernovae. So if you had asked a theorist, how do you find, would you expect to see such very bright supernovae? Because we believe these come from stars which are maybe 100 to 200 times the mass of sun. 10 years ago, everyone had said you have to go to the very early universe when the chemicals or the metals were very low, and that's how you could form massive stars. But it turns out you can actually form them next door. These are only at redshift of 1/2, and they're small pockets where apparently we can still make very large and massive stars. There are other things we have done. For example, is that we have found nearly a dozen so-called AM Canvan stars, which are 2 white dwarfs. They are circling around each other with very short orbital period, and they can generate gravitational waves in the millihertz range, as opposed to in the kilohertz range, which is the LIGO experiment. And these can be, in principle, be detected by a future mission called LISA. In fact, these will be the so-called verification targets. And again, we can see that PTF is now in an exponential growth of contributing to this. So as these 2 white dwarfs coalesce, we believe they will, because we understand GR well enough to know on what time scale they will. We don't know the outcome, so this is one of the frontier areas. So astronomers are focused a lot on how single stars evolve, but now what happens if you have two white dwarfs coalesce? What sort of new things? And it might be that some of them will produce these calcium-rich explosions that I talked about. But this is a very interesting area. In fact, one of the professors here is working a lot on the tidal effects that may happen before coalescence, because that may affect the evolution. So this is a sort of rich phase space you explore through observations. So we did this for about 2.5 years, and we said, oh, well, we've done enough of this sort of major exploration. And the idea was to now go and start seeing supernovae when they're really, really young. And as I told you, I sort of like all these manufacturing details. So one of the great concepts introduced by the Japanese automobile industries is Kaizen. Kaizen is a way by which if you want to improve a process, the physicists or scientists' approach is you look for the biggest effect. The understanding, the assumption in this manufacturing is everyone's figured out the biggest effect, that the real improvements can only come by a series of very small improvements. So in Kaizen, you say, if you want to do a 10% change, then every few months you do a 1% change by very carefully understanding. So I told Mansi at this point, I said, okay, Mansi, you have to be a bit of an engineer and talk to people and Kaizen your way through and understand how we can respond to these events in the same night. And this requires a lot of little understanding, you know, how can you move the telescope at the same time, change the filter wheel, where the delay is coming. Anyway, this was all done. So we got on to this same night response, what I call low latency science. And fortunately for us, we got this all ready in summer of 2011. And we are lucky. As I told you, it's much easier to be lucky than to be smart. And we are very lucky because nature blessed us with a nearby 1A. These are these weird supernovae, but of great importance to cosmography. And we discovered a supernova in the Pinwheel galaxy. And this is a very nearby galaxy. This is the nearest supernova we discovered in 25 years. And we discovered that in 10 hours after it exploded. I showed this picture, I forget, maybe I'd gone to the Institute for Advanced Study, I forget, somewhere, you know, there are a lot of string theorists. I did say something about string theorists, right? I said, well, can you guess which is the supernova? And I thought, oh, well, you know, they're very smart guys. They'll know when it's exploding, it's very hot, it'll be blue. Someone will show a blue star. And one very particularly bright string theorist told me, yeah, it's easy. The supernovae always come with an arrow. Okay, okay, that's a supernova. You know, as you know, the arrows are put in later by astronomers. But okay, so this object was great because with one object, we were able to bash off 2 Nature papers. And as Professor Dong Lai indicated, you get extra points if you publish Nature. Actually, the one reason I like to publish in Nature is you don't have to pay any money. Whereas if you publish in society journals, you actually have to pay money for your own paper. Which I find is irritating. Okay, so where are we now? This is a picture of the sky in the same coordinate system. Actually, this is, in the same coordinate system. And if you observe that piece of sky 100 times or more, it's yellow, it's red, it's only 1. And we've been covering this sky quite well. And there's a lot of legacy data that we can actually go and do very interesting things. Okay, in the last few minutes, I want to go and say, okay, what's next to be done? As I told you, my view is every project should actually have a definite ending. Otherwise, you'll find scientists will continue doing the same thing. I have a simple rule with the grad students on my advice. I tell them, if 5 years from now, if I went to give a colloquium in a thesis topic, I'll personally shoot you. And I guess in modern times with an AR-15. Okay, no, sorry. Anyway, okay, and the reason is that it's very tempting when you have a project which is working well. This project has been fantastic. We write a paper every 3 weeks. Got about 4 Natures, 3 Science, and in fact, it was so tempting and so burdensome to write papers. I had to take a year off just to sabbatical to get away from paper writing. But that means it's a good time to end the project, okay? And so last year we ended the PTF program and reconstituted the group to do something more focused. It's something called intermediate PTF. It's the I is a little I, and PTF fits in iPad, iPhone, IPTF. Okay. So while that's going, and that's going to do some very specialized studies where every 3 months we'll switch and try to do some interesting experiment. Okay, so the first part is to really go after we have explored the Zwicky phase space from one day longwards. So there's this whole phase space, and again, since I'm a genuine astronomer, I know there's this blank space. That means there's stuff to be found. Maybe it's not important, but there's stuff to be found. So we're on to, with IPTF, we started doing some forays here, okay? That's our main goal for this year, is to really go at high cadence, is to revisit the sky 6 times the same night and find things that are changing on time scale of. And that we'll do because that's like a pilot study. And for the future, if you want to do such high cadence studies, you have to increase the field of view. We have 8 square degrees. If you want to look at the same piece of sky many, many times, then you'll not be looking at new sky because you're spending all the time over there. So the one way you can look at new sky to find more things is to increase the field of view. So we're going from 8 square degrees to a 40 square degree camera. So we're midst of, right now we finished the preliminary study for a gigapixel camera. And the reason we can do this is thanks to Moore's law. When we started PTF to now, the cost of CCD per pixel has decreased by a factor of 3. So the money we spent, for the same money if you spend, you can get 3 times 8 square degrees. That's 24 square degrees. But we're making it a little more ambitious. The other thing is, it's one thing to get a spectrum, find a detection, but you must get spectroscopy. So we are into robotic spectroscopy. So we are building a machine that can go and do spectroscopy without a human intervention, which we call the SCD machine. We also need photometry, and we've finished this project called RoboAO, which is Robotic Adaptive Optics. And finally, I'm on this program, which our internal name is LIMSAT, and this is a UV telescope to go and find really young supernovae. So let me explain in some detail. Okay. So robotic AO, so we in fact now demonstrated on the 16-inch telescope most adaptive optic systems that are built. It's like a mission control. You have a laser engineer or laser scientist, someone who's running the deformable mirror, and someone who's taking the data. Our system, there's no one there, okay? We have a UV laser, 20-watt UV laser. From Rayleigh scattering, we form the artificial guide star, and we can, in fact, observe 250 targets a night. Okay, and it turns out there's something interesting. By switching to UV lasers instead of optical, we don't need to actually talk to the FAA. If you're using optical lasers, you may have seen a news a couple days ago, someone in California, where I live, got sent to jail for 30 months for pointing this laser at I think something similar to this at an aircraft. But it's UV, 20 watts is fine. This sort of stuff is only maybe 10 milliwatts at best, because UV is absorbed by glass. Okay, so that's all done. So here's the camera design. The current camera only occupies this much the focal plane. The new one is in fact going to be that big. Here's a spectral energy distribution machine. It uses something called an integral field spectrograph, which is all the light going through this little central square will get spectroscopy. So you can just slew the telescope. One of the discovery pipeline will say, yeah, it looks interesting. It sends a packet to the 16-inch, which then gets a spectrum. And a nice thesis project is to then take the spectrum and do machine classification, what kind of supernova it is, or if it's supernova or not. And only if it's something interesting, then wake you up or not. And here's the LIMSAT or the UltraSat, which is so the reason it was called as LIMSAT is for 25 years I worked on this large NASA program called Space Interferometry Mission. We happily spent $500 million of your hard-earned tax money, and then NASA did not allow us to go into phase CDE in 2010. And that experience made me completely allergic to all these large projects. Because you can spend your life in doing these sorts of things. Most of the time, these large projects, by the time they are actually executed, they tend to be boring, actually, in my opinion. But if you spend enough money, there's always enough publicity by the agency and by the people who spend the effort to always make it more of a success than it really is. So I said, So I wrote a proposal to a foundation. I got a $100,000 grant. So it was a one-page proposal. I said, I want to do something completely opposite, which is while the rest of the nation wants to do big things and longer things and more expensive things, I want to do something where we can launch a mission every 3 years or 5 years and do one thing, but we'll do that one thing really well and we'll do it quickly. And then I got this money, and then I assembled a group of people, 3 from India, 3 from Israel, 3 from Canada, and 3 from Caltech. We regard Caltech as a country, as you can see. There's a reason why I chose these countries. You can ask me that later. And anyway, and we said, you know, astronomy is so interesting, it doesn't matter whether it's radio, optical, UV, X-ray. You give me you can always go, it only takes 10 seconds to come up with an imaginative idea. The main problem is to find something which is feasible. And so then we came up with this ultrasat. So the name was LIMSAT, and because of the movement was called as less is more satellite. And when we were about to submit a proposal to NASA, they said, this humor may not sit well with NASA headquarters. So we called it ultrasat, ultraviolet transient astronomy satellite, or something more, you know, lame, as my teenage daughter would say. Anyway, so I've been now assembling a group of people for this collective effort. So a few years from now, I hope we'll have this armada of things, you know, one in space, 40-degree camera at Palomar, robotic spectroscopy, ultrasat will find something, we'll follow up, or we'll find something, send a signal back to it. Meanwhile, all these people doing these large, ponderous, expensive projects, they can continue doing large, ponderous, expensive projects. So I've gone around and made my siren song. Here's sort of the ZT of Gray-ware. So this is the next generation of young people that I told, come and work with me. I'll make you rich and famous. No, I meant, I'll make you famous anyway. And here's a Cornell student, Adam Woschak. He's now working on main belt comets, and soon on, that's his project with PTF, or PTF. So let me leave you with this very juicy phase space. Astronomy is so fantastic. You can actually go and build modest projects. And with a lot of enthusiasm and a bit of hard work and a bit of luck, you can actually make discoveries. You don't have to always spend $1 billion to do great science. Thank you very much.
Thank you very much. I think you agree, we don't have to agree with you, right?
It's better if you don't agree, then I can debate you.
Questions? Questions?
Shri, the LSST, which is probably coming in the future, how many supernovae they would detect per month?
I think maybe 6,000 or something. Yeah, you know, but so what? Detection is not everything. My argument with something of that sort is any project should be viewed end to end, and that's my big problem with LSST. Is let me just pretend to be God. As you know, I like being that, and then I'll say, here's I'll give you right now. I'll give you 1,000 supernova candidates, RA, DEC, delta magnitude, a little postage stamp. What are you going to do with this? And LSST people have no answer to that at all. In fact, my goal right now, and you know, even though I'm part of the collaboration, is I want to do all the 21st magnitude and brighter science before LSST happens. They'll be forced to go and do faint stuff. It'll be fun, actually.
Jonathan.
So there are other small satellite programs. There's CubeSats, nanosats, all that sort of thing. Is this modeled on that? Is there something?
No.
What do you just, what is it that you're doing?
Yeah, we looked into CubeSats, and this is not a cheap, on the project, on the scale of CubeSats, I'm sorry to say this is not cheap at all. Ultrasat is a $100 million estimate. So the Israelis are putting about $60 or so million, and we put this proposal for a mission of opportunity, which is being, in fact, today is the day I get what are the technical comments or reaction back. So maybe you want to call this a mini satellite. So this is more in the one and only UNISAT, the University Explorer, UNEX. Yes, it's in that category. There's only, so in the category of chipset, that's right.
So it's inertially pointed, low Earth orbit?
Yep. And so, okay, now I can tell you why I chose these 3 countries, because I don't have huge confidence NASA would go with this. So the backup plan is, the Israelis are actually quite good at building these inexpensive buses, which is capable of all the things that you mentioned. In fact, the bus is slightly over scope for our project. India has great launch capability, and the Canadians, you know, they're always happy to participate in a $10 million instrument. So it's like a Russian stone soup mission. Anyway, that's plan A. But plan B is the mission of opportunity. Yes?
Why did you choose to go that direction in space, as opposed to the other direction?
The long part?
Like, why did you choose to go to shorter decay paths?
As opposed to? The longer one we get for free. Brighter ones are there are many other people doing that. There are all sky, you know, there's fisheye lens projects and so on. So I don't see a competitive or a strategic advantage for us. The long ones you always get for free. That's the easy part.
Can you tell Nigaran, planetary scientists, what a fallback supernova is? Those really short cases.
Okay, a fallback supernova is, we know that massive stars explode, form an iron core in the center as they age. And at that point, the core will start collapsing because iron fusion is not exothermic in simple terms. So it'll either form a neutron star or a black hole. So there's above a certain mass, you form a black hole. And the ideas are, if you form a black hole, even if you have a shock wave that comes out, much of that newly synthesized material is in fact advected into the black hole before it ever has a chance. And therefore, we believe this is an idea, okay, that this black hole, depending on how much of the nickel is advected, it can be very bright or very faint. And that's the fallback thing. If you form a neutron star, is therefore long enough lived on dynamical scales, but very quickly it becomes a black hole. And the exact amount of or where this matter that advects into what explodes is unknown.
So you have a very sharp drop-off on a very short time.
Yes. Yeah.
Okay, so thanks very much for this provocative but very interesting